when we have perfectly elastic collisions. We said those are the situations where we have a conservation of kinetic energy. Let's consider a head-on, perfectly elastic collision between two balls with two different masses. So one ball is incident, it's moving initially, and we'll say that the other ball is not moving. And so there's a certain amount of kinetic energy in that situation. That kinetic energy is being carried by the moving ball. And if this ball is moving, it must also have an initial momentum that it has as well. During the collision, there can be an exchange of energy, but that exchange of energy has to be reversible. Basically, there's an exchange of kinetic energy between the two objects, but there's not a loss of energy to thermal energy, to vibrations within the objects, etc. And so after this sort of collision, one ball is incident, it's moving in, there's a collision, and the two balls will move after the fact. Since both of them are moving, there'll be a different kinetic energy that will be comprised of the kinetic energies of the two moving objects. But if it's a elastic collision, this final kinetic energy must be the same as the initial kinetic energy that we had. We've mentioned before, momentum is always conserved in isolated collisions. So as long as there aren't external forces acting, momentum is being conserved. And thus we can also say that the momentum at the end, the momentum being carried by these moving objects, has to be the same as the momentum that was initially there, that was carried by the initial moving object. Thus, if we're talking about perfectly elastic collisions, we know that we see that kinetic energy must be conserved as well. And so we can write that as a conservation of momentum. We have a initial velocity of the first mass. That was the only mass that was moving, so all of the momentum was carried by the first mass. After the collision, the first ball and the second ball are both moving. They have final velocities. They have different velocities than they had initially. But the total amount of momentum at the beginning has to be the same as the total amount of momentum at the end. We also have to have a conservation of energy. So we have the total kinetic energy before the collision was all carried by the first ball. So the first mass carries all that kinetic energy. After the collision, some of the kinetic energy is carried by the first ball, some of the kinetic energy is carried by the second ball. They have different velocities than they had before, so they're carrying different amounts of kinetic energy. But the total kinetic energy at the beginning must equal the total kinetic energy after the collision. This is an approximate case, this is an ideal case, but many situations allow us to approximate them as perfectly elastic. For example, billiard balls colliding. There's very little deformation or vibration, and so we can treat many real-life situations as being approximately perfectly elastic collisions. We'll see in a moment what some of the consequences are of this dual momentum and kinetic energy conservation. If we assume that we know the masses of the objects and that we know the initial velocity of the incident particle, the particle that is used as a projectile that's flying in to do the collision, then the only unknowns we have are the final velocities, the final velocity of the projectile and the final velocity of the target particle, the particle that was at rest, that is being collided, being collided with by the incident particle. And so if we have two unknowns and we have two equations, we should be able to solve and find expressions for these unknown post-collision velocities. The first thing we can do is recognize that in the conservation of energy equation, there's a common factor of 1/2 that will cancel out for simplicity's sake. But if we want to find, for example, the velocity of the incident particle after the collision, we have to eliminate the velocity of the target particle after the collision. So we'll solve for that in the first equation and plug it into the second equation. I will use a prime for the post-collision velocity for the sake of simplicity with handwriting. So we have the mass of the first object times its pre-collision velocity minus the mass of the first object times its post-collision velocity. This is the change in momentum of the incident particle, and that's equal to the momentum given to the target particle. And then we can divide by m2, cancel it out on this side so that it goes away. So here we have an equation for the velocity of the target particle after the collision. We're going to take this value and we're going to plug it into the conservation of energy equation. This is the term that we already had. We're rewriting that. Here we have a mass 2, and that mass 2 is multiplied by the final velocity of the incident particle, which we are replacing with our expression from the momentum equation. Now we can multiply this out. We'll distribute the square to the upper term and the lower term. What else we're going to do is we notice that there's a common factor of m1 that we're going to factor out as well. So there's a common factor of m1 that's being squared. There's an m2 on the bottom that's also being squared. And then the difference in velocities is being squared. What we see here is that one of the m2s will cancel one of the m2s there, so we can get rid of that. We see that there's a common factor of m1, and so we can cancel that as well. Now what we're going to do is we're going to move this term over to this side. So we subtract it away from here, and we will subtract it away from the other side of the equation as well. Now the reason we want to do that is that we see here we have a difference of two squares. We can break that up and write that as just to separate our steps, we'll draw in a line break there. But we see that this is what we had before. We've taken a difference of two squares and written them as in their factored form. What this allows us to do is we see that we have a common factor that cancels out there as well, and we can get rid of those terms. We're going to go ahead and multiply both sides by an m2. Because now the m2's cancel as well. We're still trying to find v1 prime, v1 after the collision, in terms of the velocity before the collision, and we can do that here. We will distribute the mass terms. We'll now move this term. We will group our v prime terms together. We'll add them to both sides. And that will cancel out on this side, so we can eliminate that. We will subtract the non-v1 prime terms So we subtract it away from that side, and it goes away from there as well. Now we have all of our v1 prime terms on one side, our non-v1 prime terms on the other side. We'll do a little bit of factoring here for simplicity. So then v1 prime is equal to m1 minus m2 over m1 plus m2 times v1. So there we have a relation for the velocity of the incident particle, the velocity of the projectile particle as a function of the velocity of the incident of the particle before the collision, the same particle before the collision.